Hello everyone. So, we will continue with our present topic fiber reinforced composites. So, in earlier classes I have discussed the basic understanding of composite, then different existing manufacturing techniques and also the hybrid yarn manufacturing techniques for producing composites. Today we will discuss another method of manufacturing composite, which is thermally bonded roving methods of manufacturing composites, mainly from natural fibers. Okay. So, if we see the composites, as I have already mentioned, these are of mainly three types based on the matrix, that is metal matrix composite, ceramic matrix composite and polymer matrix composite. So, advantages and disadvantages of thermoplastic and thermoset matrix we have discussed, and main advantage of thermoplastic matrix is that we can reuse the matrix once again, and also in absence of the biodegradable polymers, at present we can produce biocomposites using thermoplastic matrix, at least to some extent we can save our environment. So, that is why we may call it as biocomposite. So, what is biocomposite then? It is a range of material of which partly or fully derived from low environment impact sources. So, at present what we will discuss a manufacturing method of composite, where component like at least 50% of the composites are made of natural fiber. So, at present we will discuss the flax fiber, which is biodegradable, and the matrix component, here we will discuss the thermoplastic fiber, that is polypropylene, where if we want we can reuse the matrix once again. So, as it has already been mentioned, the textile fiber we can divide into two broad classification. So, these two classes, one is natural fiber, another is synthetic fiber. So, at present what we will be discussing on natural fiber, and that is vegetable fiber. So, natural fiber is subdivided into three categories: animal fiber, vegetable fiber, mineral fiber. So, the present day biocomposite we manufacture mainly from natural fiber, which is vegetable fiber, natural vegetable fiber, and here we will discuss the flax fiber, which is used as reinforcing material in manufacturing biocomposites. So, as far as matrix is concerned, polymer matrix particularly, so they are of mainly two types. One is petroleum based polymer, another is biodegradable polymer. So, petroleum based as already been discussed, it is of two types, one is thermoset, another is thermoplastic. So, thermoset, the limitations are they are non recyclable. So, once the composite is manufactured, they cannot be reshaped or reused again, limited storage time, longer curing cycle and corrosive to handling. So, these are the disadvantages. Due to that, the present day composites are focused towards the thermoplastic polymer, and if we try to use 100% biodegradable polymers, the main drawbacks are their limited availability. They are not available in large quantity, and another drawback is that their cost. So, high material cost to service life ratio. So, their service life also low and at the same time high cost. So, the alternate way, the only way at present we can use thermoplastic polymer as the matrix material. So, their advantages are high toughness, high chemical resistance, high strength to weight ratio. So, if we take the certain mass, their strength we will get is relatively high, and most important is that they are recyclable. So, hence in the present development we have used thermoplastic polymer as matrix to manufacture composite. Okay. So, the basic driving force towards this direction is that disposal of solid waste. So, disposal of solid waste is the biggest problem. So, once we manufacture composite from thermoset polymer, after use the disposal is main concern. So, we cannot reuse that. So, other driving forces are development and use of biocomposite fits well with the protection of environment, and biocomposite we can reuse again and again, but before we go for manufacturing biocomposite using natural fiber, natural vegetable fiber, there are different drawbacks also. What are these drawbacks? The main three drawbacks are poor interface bonding between natural fiber, which is basically they are generally hydrophilic fiber, and thermoplastic materials, they are in general hydrophobic. So, their interface bondings are relatively weaker. So, that is the main concern. Next problem is that short fiber. So, natural vegetable fiber if we talk about, we always get in short form, not continuous form. So, their orientation, it is not along the axis. So, the control of orientation of these natural fibers are very important, because we can only get continuous strand from natural fiber is by twisting. Once we twist, the fibers are aligned at certain angle, so that we do not get the proper strength realization. And third point is that non-uniform fiber resin distribution in the composite surface, because in the composite structure, due to high melt viscosity and the fibers are being twisted. So, due to high melt viscosity, the penetration of molten polymer inside the core of the yarn is very difficult. So, we have to overcome all these three drawbacks before we go for manufacturing biocomposites using natural vegetable fiber. So, the approach is that we have produced hybrid yarn. Hybrid yarn means, as we have already discussed, where the matrix fiber and reinforcing fibers are mixed evenly together, so that the flow of polymer, it is very short, the flow length is very short. So, they are already inside the structure, and the first problem, poor interface between the natural fiber and thermoplastic composite, is overcome. This problem is overcome using the by surface modification. Okay. So, these problems we can overcome. So, as I have mentioned, we cannot form continuous strand from staple natural fiber without any twist. Ideally, if we get the fiber strand like this strand of parallel fiber, so in that case the penetration of polymer will be easy. Now, let us see in at the present stage our approach is that suppose this is normal staple yarn. Staple yarn, as I have mentioned, we cannot manufacture staple yarn without twist. Now, suppose this is flax. Now, suppose we want to now manufacture composite using polypropylene. So, polypropylene matrix, if we try to push inside the structure, it will be very difficult, because the melt flow index of polypropylene is very high. So, it is not easy for the matrix to penetrate inside the structure. So, another problem is that when once we twist, the fibers are at certain angle with the load direction. So, we do not get proper strength utilization. On the other hand, if we can align the fibers parallel to the axis, that means 0 twist. Zero twist, in that case the penetration of matrix will be easier, because the fiber to fiber distance is high. So, there are space, these spaces they can, the matrix can enter easily, but the problem is that it is not possible, because we have to have certain strength for handling the material. So, what is the alternative? In the present approach, what has been done, the rovings made of flax and polypropylene fibers these are the flax fibers, here these are polypropylene fibers, and here if you see again we have 0 twist, but after making the polypropylene and flax roving, we treat with heat. This heat treatment melts the polypropylene, this PP, they get melted, at least surface polypropylene fibers were melted. So, they form a continuous strand, these are say melted polypropylene, and the flax fibers remain. So, this prepreg or toe preg, this is because if we can call it as toe, this is a toe preg. So, this toe preg we call it as TBR, that is thermally bonded roving. This thermally bonded rovings, they have got proper flexibility and we can use in the weaving machine, and they have got certain strength also. So, as has been explained, the twisted based yarn. So, this twisted yarn here, due to the alignment, the strength realization is low, although the twist improves the handling of the material, but it reduces ultimate fiber strength utilization by factor cos theta. Also, it restricts the resin penetration into the bundle. As has already been mentioned, that hybrid yarns can be manufactured using ring spinning, that is core sheath structure we can manufacture, rotor spinning, drape spinning, braiding, commingling. These are the different methods of manufacturing hybrid yarn. So, basically hybrid yarns are the yarns where more than one components are there. So, a hybrid yarn contains both matrix and reinforcing components within the structure, and it reduces the effective resin flow distance during composite, which is very important because the thermoplastic composite they have very high melt flow index, and the hybrid yarn improves thermoplastic resin distribution in the composite structure, because both reinforcing fiber and thermoplastic matrix component fiber they are already present inside the structure. So, the void content reduces. Why? If we have the matrix fiber within the structure, so the chances of void content will be less, because already the penetration of matrix components are there inside the structure, they have already penetrated. Main drawbacks are low rate of production. So, hybrid yarn production it is a little bit slower rate. Natural fibers in the hybrid yarn remain in the twisted state at present, but our new approach we have overcome that problem, and main problem remains is that distortion of yarn structure and random yarn breakage takes place during weaving of hybrid yarn. If we want to reduce the twist to have better penetration, the strength reduces, and during handling, during weaving, the hybrid yarn breakage takes place. So, the main solution here is that both the reinforcing and matrix forming fibers should be there in the hybrid roving structure to have lowest possible resin flow distance. The natural fibers in the twist free state, they are highly aligned to the axis of the roving, and we have to develop the yarn or roving structure in such a fashion that they are suitable for weaving to make textile preforms. So, this novel structure which we call it as thermally bonded roving TBR, and it has been developed using a newly designed machine. We have modified the existing setup, and what we have done, we have evaluated various properties. Like one question is always asked that thermally bonded roving, can we weave into a woven fabric? So, for that we need to study the weavability study that has been done, and that various other properties we have studied, that is flax fiber content, proportion of flax fiber content and degree of mixing, how all these parameters affect the unidirectional composite properties, UD composite properties. So, after that, after making the unidirectional composites, what we have done? We have produced oven prepreg. So, oven prepreg means in that oven structure already the matrix and reinforcing components are present, and after that, after making the oven prepreg, we have made the composite laminates by layered technique. So, TBR based oven composite laminate properties are compared with the glass PP composites. So, glass PP composites, they are very common and it is easily available in market commercially. So, what we have done, the developed composite made from the thermally bonded roving of flax fiber. So, we have compared with the existing glass PP composite. This is the schematic diagram of the setup which has been developed. So, this is here feed sliver can. In this we can have a number of such cans where the flax sliver and polypropylene sliver, they are fed through the this guide roller and then through the feed roller, and ultimately it is going to the gill drawing system which is used for long staple spinning system. So, this gill drawing system is used because we are using long fiber, flax fiber. So, we have taken the polypropylene fiber also in the longer cut length, so that both flax and polypropylene, they are compatible. And we have processed this flax and polypropylene slivers through the gill box a number of time, and that detailed study we have done, and we have studied the effect of number of passages. Number of passages means the more the passages, more will be the uniform blending. So, higher blending is required for proper composite manufacturing. So, after that, at the last stage what we have done, this roving, they are processed through the plate heater. So, this is the photograph of the gill drawing system, where we can see this white color slivers are polypropylene and this brown slivers are flax, and these combs are, these are Fowler bar of the gill drawing unit. So, after the final roving is passed through the condenser and guide roller, and when it is passing through the plate heater and condenser. So, this is the condenser and blended sliver, and here the temperature sensor. So, this is the heater, and we get the roving with a flax which is in the form of fiber and polypropylene which is molten. Here we can see that polypropylene fibers at the surface of the yarn are melted and the fibers, polypropylene fibers which are in the core, they are still in the staple fiber form. So, there is a partial melting and which helped in having higher flexibility, it retains the flexibility. At the same time, due to melting, the strength of the strand, that is roving, is such that it can sustain certain load. So, this is the cross section where flax and flax, these are the flax fiber, here are the polypropylene. So, this rovings, they have certain strength characteristics such that we can develop oven prepreg, and this is called TBR, thermally bonded roving. And if we see here, the fibers are almost aligned towards the axis of the roving. So, we have done detailed study. I will show here in short the study what has been carried out. Now, the main question is that what about the uniformity in blending? So, to have uniform blending, we have used a number of drawing passages. So, 2 passages, 4 and 6 passages, 3 passages we have used here, and also we have varied the natural fiber flax content in the thermally bonded roving. So, which is 40%, 50 and 60, 3 different natural fiber content we have varied, and also we have used 3 different temperatures. So, that the melting, proper melting of polypropylene takes place. This temperature is the temperature at the this heater, it is 180 degree Celsius, 195 and 210. After this experimentation, we have got the response, and in box banking we have developed 15 samples of different combinations, and if we see in these different combinations, tenacity, modulus, flexural rigidity and weavability, that is number of cycles it can sustain before it breaks. So, these parameters they vary widely for different combinations. If we see this tenacity in gram per tex, it is basically it is 0.1998, as low as 0.1998, and it can go up to say 1.56, 2.35. So, this is the range of modulus, tenacity. See modulus, if we see it is as low as say 28 or 9.66, and it is going up to say 120. So, this is the range of the responses. Now, what is happening when we change the number of drawing passage? If we see, we have placed the flax and polypropylene side by side. So, this are the flax, okay, the brown color, and green color, these are polypropylene, and after fast drying, if we see, they are not mixed enough. So, their identity remains, and even after second drying, we can very well see the strands of flax and polypropylene. But once we increase the number of drying passages to 4, this becomes little bit mix up, but here the polypropylene rich and flax rich portions can be seen. It is easily visible here, polypropylene rich segment and flax rich segments, although their continuity has been broken. But if we further increase the number of drying passage to 6th drying passage, after 6th drying passage, what has been observed, that the flax and polypropylene fibers have been mixed uniformly. Now, if we see the actual photograph, so after second drying, so 2 drying passage, we can see this portion is polypropylene rich portion, this is the flax rich portion. So, I can go back to the earlier slide, here see polypropylene rich portion and it is a flax rich portion. So, this identity remains here. Now, after 4th drying passage, although the continuity has been broken, but here if we see this portion, bright portion, whitish portion, this is polypropylene rich zone, here it is a flax rich zone. So, that is shown here. So, polypropylene rich zone and flax rich zone, this type of things happen. But after 6th drying passage, it has been observed that this polypropylene and flax, they have been evenly blended. If we see the response curves for all these 3 variables, this is the effect of temperature and natural fiber content on tenacity of roving, which is prepreg. So, at constant drying passage, so we have kept drying passage here 6 drying passage as a constant drying passage, and if we increase, and in this axis the temperature is constant. So, at this stage if we see roving tenacity increases with increase in natural fiber content. So, from 40 to 60, if we increase the natural fiber content, which is basically reinforcing component. So, if we increase the reinforcing component up to say 60%, so from 40 to 60 it is continuously increasing, but this trend may not be same if we further increase to 70-80%, because the matrix has to be there, matrix component has to be there, because the fibers are in parallel stage. Now, if you see this axis here at constant drying passage of 6 and natural fiber content here say if it is 40%, roving tenacity increases with the increasing thermal treatment temperature. That means, proper melting of polypropylenes are there. So, similarly, we can have different trends for different parameters. So, I will go quickly. So, here at constant drying passage of 6 and temperature, the roving modulus initially decreases with the increase in natural fiber, and after that after 50% it increases sharply. And as far as the temperature is concerned, if we increase the temperature, the modulus increases, because again due to proper binding of flax fiber with the matrix, because as we increase temperature, so melting takes place, more and more melting of the polypropylene fiber takes place, they are binding the flax closely and properly. So, it increases the modulus. Similarly, roving flexural rigidity, effect of number of passages and natural fiber content. So, here temperature is kept constant at 210 degree Celsius. The roving flexural rigidity increases with increase in number of drawing passage. So, flexural rigidity increases as the number of drawing passage increases, the proper blending takes place and proper alignment of flax and polypropylene fibers are there, and proper binding of flax fibers will be there. So, it increases the flexural rigidity, and effect of natural fiber content and temperature on roving flexural rigidity, this is the thing we have discussed again. So, as the at a constant drawing passage and natural fiber content, roving flexural rigidity increases with the increasing temperature. Okay. And if we see the roving weavability, so effect of temperature and number of passages at constant natural fiber content, say we here we have kept the natural fiber content at 60% and at same number of drawing passages, the weavability increases with the increase in temperature. That means, the proper binding of natural fibers are there. So, it enhances the strength and thus weavability increases. On the other hand, here with the increase in number of passages, we have proper blending, proper binding of the natural fibers are there. So, weavability also increases here. Now, we will study, we will see that effect of the flax PP thermally bonded roving once we produce composite. So, here we have produced unidirectional composites and we will try to see their characteristics. So, this roving what we have produced thermally bonded roving, from there what we have done, we have initially used this thermally bonded roving for manufacturing unidirectional composites, and in next stage we have done that weaving and we have used this oven prepreg to manufacture composite once again. Now, if we see here, our next approach was that these are the flax fibers, this is thermally bonded roving and these are the matrix component. These are the polypropylenes, at the surface it is molten and we will use this thermally bonded roving for manufacturing unidirectional composite, like this is, these are the thermally bonded rovings. at this is 1, 2, 3, 4. So, 1, 2, 3, 4 such number of rovings we will put together, and if we see the cross section. So, this is one layer, then after that we will put polypropylene film, then another layer polypropylene film, another layer. This is basically TBR and this is PP film. So, and to have certain thickness, and after that we will do compression molding. So, this compression molding and we will get the composite. And second approach, this is approach 1, and second approach will be our, and this TBR is a prepreg for manufacturing composite. And second approach is that we will use this TBR, this is UD composite, unidirectional composite, where fibers are parallel to the axis. And in the second approach we will use this TBR, thermally bonded roving, to manufacture woven fabric. So, this is UD composites, this is plain woven fabric, we will make. So, in next class we will discuss this two different types of composites. Till then, thank you.